Welcome to a presentation on big data and graph-based deep learning. So our group did a project around using big data to generate drug, help discovering drug, and especially around COVID-19. So our team, Kanishka, myself, Tim, and Vlad worked pretty hard in the last couple of weeks to use different models to generate new COVID-19 drugs. And let me walk through the process. So before I jump into anything, let's talk about why is this important? Why is this? Why do we do it this way? So currently, when we try to find a new compound that is a possible drug candidate, the most promising method that we have is to use fast screening method. The idea is that out of the 10 to 23rd to 10 to 60th compounds, we select about like 10,000 each time to go through the screening process and do different tests around it and small tests too. And it's very difficult because you're selecting very little tiny amount of compounds to do drug discovery. And a lot of the times it's a miss and also takes a lot of resources and time. So our idea is that since we have existing data sets, why can't we do something like, for example, deep learning model to use existing drugs to generate new compounds? And knowing that, we set up this process of how to improve drug discovery. So first we grab a drug data set, and then we do any extract transform load around it to generate new features. We use those features to train the model drug data set. And then you use validation, for example, use a QED score to look at how likely something to be a drug. And then we also validate the result by similarity. So how similar your generated drug and your original drug is. And then we input existing drugs, like the one used to treat COVID-19, and generate compounds that with like a really high drug likelihood score. And then at the end, we'll suggest this set of compounds to the authorities or pharmaceutical companies to help speed up drug discovery process. So we're talking about like, selecting instead from 10 to 23rd to 10 to 60th compounds, they can do something like 10,000 or 100,000 drugs that they should try first. So the data set that we use is a Zinc data set. It's a non-commercial data set that has like 827 million compounds. You can use the data sets to generate a lot of interesting features like the encoded string, the QED score, the log P molecular characteristics, etc., etc. So it's a very useful database, and you can see it has a tons of variety in the database as well. It's not focusing on just one or two band of like QED score drugs. The way we do it is that we have to scrape it from the same data set. So it's stored across the many text files. So we have to download it, we have to scrape it programmatically and load it into a PySpark data frame. And we use PySpark data frame for streaming data processing. We calculate all the necessary features, put in the column, and then we use those features to fit into the model. And then this is some characteristic that we found, while looking at the Zinc database, and this is the columns that we generate. And some of it is around like COVID-19, so you can see how COVID-19 has different QED score and also molecular rate. Before I talk about the model, I want to introduce a concept: what is graph-to-graph and junction tree, and how it's related to the model. So imagine there are two graphs. Graph-to-graph is something that, given an existing graph, generates something that's similar to it. And if you look at it, you can see on the left there's a molecular graph, and on the right there's a decoder graph. So you use the graph on the left to generate graph on the right. Quite simple. We're using traditional graph-to-graph techniques. You never go from the left to the right. The reason being, when you do graph-to-graph, you look at, okay, what's the next node that I can add to the graph and make a new graph. However, in chemistry, when you add a compound, for example, a hydrogen in a ring, you could never just add one hydrogen. That's an unstable chemical compound. So you would never add a ring to an original graph to a new graph, such in the example. So the idea that we have to create a minimal tree, a junction tree, that encapsulate all this like chemical information to generate a graph that you can add things to it. So for example, you encode it into a junction tree here in the example, and then you do deep learning, you generate something that you can attach a ring to it. and then you decode the junction tree to get your full graph. Then you can go from the graph to the left to the right. Using this concept, we deploy two different models that we have, the graph-to-graph, G2G, and a hierarchical graph-to-graph, HG2G. The differences here is that one in the deep learning step will use a message passing network, and on the other one, we use a LSTM-RNN model to generate the new graphs. And the results is quite similar in both cases. In G2G, you can see, and HG2G, they have very similar similarity average and the average QED. However, in G2G, only 3/7 of the set fit into our filtering criteria, which is you have to be more like a drug. So QED delta has to be larger than 0.1. Meanwhile, you want to be similar to the original drug because we know the original drug works and you want to generate something very similar to it. And in this case, HG2G does a much better job into generating possible drug. So around COVID-19, we want to increase or improve on the original model that fit into the COVID-19 a bit more. The idea is that there are 8 COVID-19 drugs from the same data set that is known to use to treat COVID-19. And then we want to generate new candidate compounds to be screened for future possible drug that treat COVID-19. Because of this, we introduced something, a filtering process, our team's filtering process, alongside with HG2G to improve the selection. The idea is that we want to pick out drugs that's already similar to COVID-19 drugs and use it as a training set instead of just fitting the whole thing. And you can see the result here. Applying the filtering increase the similarity and the QED score that around COVID-19 drugs than comparing to no filtering method. One of the results that we found, EIDD 2801, we generate a graph that is really similar to original compounds. So you can see using a native method, you get a very different compound. Although it's highly likely to be a drug, it might be treating something else. Versus we have a drug that is highly similar to the original graph, while it's less likely to be a drug, but is as an alternative to find a newer result. So in the future, we would like to try out larger compounds and just like search for more molecules. And that's conclude our project that we worked hard on in the last couple of weeks. If you have any questions, feel free to email one of us. Otherwise, thank you.